All right, welcome back. I hope you enjoyed your break. I also hope that I didn't scare you too much with the schemas, and in particular XML schemas. Now we'll go to an easier part, because this part is going to be visual. And in fact, this is the part that will be the most important for the rest of the lecture, for the continuation of the lecture. So by now, you realized that you can have XML or JSON billion of these objects thrown on HDFS or on S3 without any validation, then it's a big mess. But what you typically do in the preparation process, when you have a data set, that you clean it all up, basically, you rearrange your data in such a way that it has structure. And when you are done cleaning things up, the next step is to design a schema, and then you validate your data, JSON or XML, against your schema. And then you have this structured collection of documents that all look alike. And what you get, in essence, if you started with JSON and used JSON compact schema, you end up with a data frame. That is the one thing to remember, right? So let me explain. So let me start with a table. So a table has rows and columns. This is in the first normal form, right? This has atomic integrity because there's nothing nested. It's just rows and columns. So this is the sort of things you will find in PostgreSQL and any relational database as well. It turns out that you can express this also in JSON. I showed you earlier how to do that. And the schema that you would have associated with that is an ID that is an integer, a name that is a string, a living column that is a Boolean, true and false, right? So I hope you agree now that this JSON schema, so you see it's very natural to express, this JSON schema, if you apply it to a collection of 4 JSON objects, gives you visually that table, right? So it's one JSON object here, second JSON object there, a third JSON object, and a fourth JSON object, except that, of course, now I'm not showing JSON anymore. I'm showing the actual nice, tidy representation. This, in fact, is called a data frame. Well, you will tell me, okay, that's also a table. Yes, but a data frame is more generic than a table, because a data frame can also be denormalized. All right, so let's go to something slightly more complicated. So, okay, now this is relational databases. Let me change this a little bit by saying, okay, now name is not just a string, it's an array of strings. So in the JSON compact syntax, that's very easy to do. You just use the array notation and say, okay, it's an array of strings, just like that. That's really just a template, right? It almost looks like the actual JSON document when you do it that way. Well, how do I represent it? Well, how do I represent it in the data frame visual? Well, I denormalize my data. It's no longer a table now, right? Because now I have these lines that don't go all the way, right? So you see, it's in Excel, I actually had to do merge to prepare actually that visual right there. This is denormalized. How do I see it? Well, it's because here I have one tuple, so this is one JSON object, but in here, associated with name, I have an array of 2 values. I have Albert and Einstein, right? A name can have the first name, the middle name, the last name, and so on. Visually, the way I show it is that I add the horizontal line right there with the first string that is right there and the second string that is right there, right? And then living is again a Boolean. So you see here, it's an array with just one string, 10 rows. Here it's an array with 2 strings, Alan Turing, and here it's an array with just one string, D. All right? So this is my example. So you see, it's denormalized because you see this nested structure in there that you wouldn't have in a normalized table. And this is a data frame. This is what you can do with data frames. So in data frames, what is new is that the type of a column doesn't need to be an atomic type. It can also be a structured type, and in that case, an array of string. And here you see an array of string. That is the first sort of things that you can see in a data frame, all right? Let's look, so okay, this was a nested array. Let's have a nested object now. What is a nested object? Well, here's an example. Okay, it's again JSON. It's super simple to understand. You have ID that is an integer. You have name that is an object, and that has 2 nested values, the key first associated with a string, and the key last associated with a string, and then living that is still a Boolean. So I just changed, instead of an array here, now I have an object with first and last. How does it look like? visually in there? Well, what I do is that I add these two headers below name, that is first and last. These are my two keys here. And now I have, okay, ID is 1, name.first is Albert, name.last is Einstein, and living is true. So you see, it's also a kind of data frame, except that this time what is denormalized is the fact that I have a nested structure in there, that I have subcolumns. You could call them subcolumns, right? Why can I draw JSON? JSON is basically some very complex text, right? How come that I managed to draw this sequence of 4 JSON objects so nicely with just rows and columns, and straight lines? It is because these 4 objects are all valid against that same simple schema. This is the reason why I can visually draw it like that, and again, have something that is called a data frame. You can even take it to the next level with actually nested tables. So what is a nested table in the JSON model? We also already saw that. A nested table is when you have an array of objects, right? This is a nested table, because now you have a table, the nested table has the columns name and type, right? And it can have plenty of tuples that are each objects themselves in an array. And this is how you nest the table. So you see, here I have a nested table. Here I have a nested table, and so on. But since the nested tables all have the same schema, I'm putting here always the same subcolumn, name and type visually in my headers. So what does it mean here? I have, you see why it's valid. ID here is an integer. Well, who is an array of objects. So who is an array of objects? The first object has the name Albert and the type first. The second object here has the name Einstein and the type last. And then I have living, which is associated with false, right? Here, what I have is an array with just one object, name, fun rows, and type last. Here I have again a third JSON object with a nested array of 2 objects. Name Alan, type first is the first object. Name Turing, type last is the second object, then living false. And then I have a fourth JSON object, and here it's an array of just one object, named in type last. This is again a data frame, but now even more complex, because again, I have objects in an array. That is the way you model nested tables, right? So this is how you denormalize data. Now you have tables in tables in tables in tables in tables, and this is something you can do with data frames. Data frames have become extremely popular in the data science community. For example, you might have heard in Python of the pandas library that is very popular. Well, this is the sort of things you can actually do in pandas, right, with Python. But again, what I want you to understand in terms of data modeling is that from our perspective in this course, a data frame is a validated collection of JSON documents that all look alike. And as a consequence, you can represent them in that fancy way. This is what you should see in your mind when you see the JSON documents. So I have a few examples to show you regarding that, a few visuals to really contrast and really make sure that you understand that, because this is very, very important. So let me zoom out. What is a data set? Well, there can be plenty of data sets that you can store. A data set can be in JSON, in XML, and so on and so on. But when you deal with a big data set, typically, from a very abstract perspective, using these abstract data types I told you about, a data set is a list of maps, right? In the case of JSON, it's a list of JSON objects. In the case of XML, it's a list of XML elements or of XML documents. In the case of a relational table, it's a list of tuples, right? A relational tuple is a list of tuples. So you see, every time a data set can be seen as a list of maps. This is the super fancy, and you know, if you want to sound smart, this is how you would put it, right? Okay, so for example, in that case, that's a flat data set that is a list of 4 maps. This is the first map, the second map, the third map, the fourth map. But again, we don't call them map. In that case, we would call them tuples, right? If it's in JSON, these would be JSON objects. If it's XML, these would be XML elements. But you see, from an abstract perspective, that's just the beautiful visual that you have here. Now we have nested data. So we have here a table that has 3 columns. And here, that third column is itself a table inside. I didn't draw it in the data frame way right now because I don't have a schema yet. So you see a table in a table. This is a list of 2 maps. This is the first map, and this is the second map, right? A map, why? Because it's mapping ID to 2, profession to computer scientist, and people to that table. Again, map is just a synonym for tuple, a synonym for objects, you know, but map is just the fancy abstract way of calling that. All right. Now I'm just switching between these 2 representations because this is very important. This is the visual of a table. This is what it would look like in JSON. It's very important that you understand when you see a data set like that here, you should see that table. It's very important. Who sees it? Can you raise your hand? Who sees that this is this visual?
Yeah, I see a lot of hands.
Very nice, very nice. So you got it, right? So a collection of JSON objects, they are all valid against some schema. Here, obviously, you can draw them in that way. So here, what happens here is it looks the same, except here we have an array of objects, you see, and here an array of objects. So you see, this is how I get this nested structure right there, because in JSON, this is what it looks like, right? So this is the physical layout as you store it on HDFS. And this is what you should see in your minds, the abstraction of the data set. And it's much easier to query your data if this is what you see in your mind than this, right? This would be much more complex to visualize. So you really need to visualize this in that way. Okay, now I showed you nestedness. Let's look at the other, heterogeneity. This is a homogeneous data set, lines and columns, rows and columns all filled. This is a heterogeneous data set because I have missing values here and I could even have extra values and so on, right? So this is heterogeneous. How do you see it in JSON? Well, homogeneous just means that you always have all of the keys. Heterogeneous means you have missing keys. Here you have living that is missing and profession that is missing. Here you have profession that is missing. So you really need to understand that this is visually this, and this is visually this, all right? It's very important. This is heterogeneity. And now you realize that JSON has this power of expressing nestedness, and JSON has the power of expressing heterogeneity, and this is the visual. Okay, now if you merge the two, you can have something that is flat and homogeneous, that's a relational database, and you can have something that is an absolute mess that has nested data and that is heterogeneous. So this is a huge mess, right? But you can see in JSON that works. You can look at it offline, but basically this visually corresponds to this JSON, right? So now you should have an intuition when you see a JSON data set like that, okay, that's flat and homogeneous. When you see a data set like that, well, the first thing you should see is that it's an enormous mess. So you obviously need to clean that up, right? But what you see is nestedness with nested objects in arrays and heterogeneity, because you see that it's not even the same sort of things you have in your array right there. Okay. Okay. So it turns out that JSON is the most intuitive way of looking at it. So this is why I showed you JSON, but actually you can do the same in XML, right? But again, I'm trying to shield you from that because I'm focusing more and more on JSON. But you could express this, which is JSON, also in XML. It would still be this visual, right? So in a way, we don't really care if it's JSON or XML. Once I have my abstraction, this is what I'm manipulating. Okay. It turns out that JSON and XML are just two of the many formats. There are many, many, many others. Data frames, that's the logical abstraction, right? The pandas library and so on. So you have JSON, XML, you have CSV. This is only if it's flat. We saw CSV must be flat and usually homogeneous. We have YAML. You could also maybe just for fun, try to store your data as YAML and so on, but you could still build data frames with that. Protocol buffers is a technology invented by Google that is pretty much the same thing as JSON and XML, except that it's more efficient and more compact. It's a binary version. Parquet, I'm going to say a few words about that, is a bit similar in the sense that it's a binary, highly compressed and efficient version. But basically, what is Parquet? It's a binary format from data frames. Avro is just another one, another technology. But the really, really, really nice thing here is that if you understand at the data frames level, the logical abstraction, all of these are interchangeable. You can go from one to the other. It doesn't really matter which one you use. Right? more or less. They have a few differences, but this is the idea. So the one thing you need to understand is the concept of data frame, and then you can store in plenty of ways. In fact, in reality, what data scientists do or should do, it's actually a good practice. If you just downloaded a very big JSON data set from the internet, maybe that's 30 gigabytes of JSON data, and you want to query it in order to analyze it, the first thing that you should be doing is to validate your JSON document, get a data frame out of it, and immediately convert it back to Parquet. If you have a valid schema that that is simple enough, you can do that. So you can convert JSON to Parquet. What do you gain out of it? Well, maybe you had 30 gigabytes of JSON. Now you just have 2 gigabytes of Parquet. So you basically compressed it, and now it's using less space. The consequence is that all your queries will be much faster. So you will spend less time waiting for your queries to complete. And that's one of the first things you should be doing in future projects. If you have projects at ETH later, you have a JSON data set, convert it to Parquet, and then use the Parquet binary format in order to query it. So how are the format categorized? Some of them allow you to nest, JSON and XML, Parquet, for example. Some of them must be flat. CSV is an example that cannot nest. CSV must be flat. Another thing that is distinguishing them is there are text formats and binary formats. Text formats, CSV is text, JSON is text, XML is text, YAML is text, right? And there are binary formats, binary formats. So binary, Parquet is binary, Avro is binary, protocol buffers is binary. Binary is absolutely great because again, it's optimized, it's compressed, it's faster. So there's plenty of advantages of converting your data to a binary format for the purpose of query, right? Okay, and finally, schema required or optional. JSON or XML doesn't need a schema. If you don't want a schema, that's fine. You can just store an enormous mess of JSON and XML data without any schema that will work. But with CSV, you need a schema. With Parquet, you need a schema. With Avro, you need a schema. With protocol buffers, you need a schema, right? So basically, these are the 3 dimensions against which you can basically remember these formats, right? Nested or flat, text or binary, schema required or optional. Right. Okay, now, why am I showing you this? Because you are going to tell me that's yet another list of types. How are we going to learn that? And that you're just throwing at us so many different things and so on. What do I want you to see here? What I want you to see is that Parquet is no different than any other format. Parquet has types, and it's pretty much the same types that we saw in JSON and XML. You see, what do we have? We have Boolean types, we have numbers, we have strings, we have binaries. There's nothing new in there. The only thing that is new is how they are called, right? This is the only thing that's new. But I warn you, it's like Swiss German dialects, right? You just call them differently. It's called int32 instead of int64 instead of long and so on. This is just a dialect. What you have to see here is that once you know this generic way that the types work, learning Parquet or Avro or protocol buffers or anything else is super easy because these are always the same sorts of menus. These are always the same categories of types. So you have absolutely no difficulty learning a new format. This is again Parquet. What do I want to show you here? That it also has arrays and objects, but it just calls them lists, the arrays, and it calls the objects maps. And actually, this is great because it actually uses the abstract names. It actually uses list and map, actually, which as I told you, these are the abstract mathematical names. All right. But again, there is no surprise here. Parquet supports objects and arrays just like JSON. Okay. And then I have to show you, because this is actually beautiful, why is that called Parquet? Parquet is a French term. It's also called parquet, I think in German. It's basically what you have in your living room when you have wood. Well, it's because the way it's stored, it's column by column in the way that it's stored on the disk. And of course, that's why it's called Parquet, because this is basically the layouts that the way you store your data frame. It basically stores a data frame a bit looking like Parquet. All right, I'm done with the data frames. And again, the one most important deliverable of that lecture is data frames. You must understand that if you take a huge collection of JSON documents, you clean it up, you structure it, you validate it against some schema, that gives you a data frame. You can store it then in a more optimized version as Parquet, and then you can go ahead and query it, but then what you manipulate are data frames. And data frames, we will see them again when we look at Spark later, Apache Spark, we will be using data frames. The beauty of data frames is that you can use high-level languages in order to manipulate them. I promise to you, it's much easier than Python to manipulate data frames with high-level languages. So this is what we will see later, right? All right, so I hope that now you have the visuals and the intuition for data frames. If you didn't get all the details of the names of the types and JSON and XML schema and JSON schema, don't worry, because there's exercises. That's the point of exercises, right? So you'll have exercises that the TA team has prepared, and you'll have an opportunity to dive more into these schema languages, right? Okay, so do we have any questions before I stop the recording for that part? Then we move over to my previews.
Seems not.
No questions? So I didn't scare you, or maybe you're just scared because of everything that I threw at you. No questions? Never hesitate. I'm here for questions if you have questions. I realize that my tie is actually similar to the Parquet behind. It's just a coincidence. All right, no questions? Okay, so let me stop the recording, and I'll see you on the other side in a few seconds where we'll start with map reduce, right? So see you in a few seconds.